My friends, I woke up at 5:30 this morning. It's 6 o'clock right now in the morning, and I'm just amped up to go through these exam problems. I don't know. I'm such a nerd. I was thinking about it last night, and I got a number of problems that give all of them a little bit different subtleties. And we're going to start off with some common exam problems, but make sure to watch to the end because the last one's a killer exam problem that has some important points to go over that your prof might catch you on. But we're going to start with this one here. So we'll start here. So when 1.3 times 10 to the 5 kilojoules of heat is added to a balloon, and actually, you know what? We'll start with a picture. We have a balloon here, and we have energy as heat going into it, and the volume increases from. So this is initially it's four. This is. Whoop! I don't want to write over that letter, but this is our initial volume to our final volume, 4.5 times 10 to the 6 liters. So we have this changing volume, and this is our initial volume, this is our final volume, under a constant pressure of 105 kilopascals. So this is our pressure. Now it's constant, which means it's going to, and this is a balloon, so it's going to be equal to the atmospheric pressure. And we want to calculate the change in internal energy in kilojoules. Well, okay, now see how I go through this question? I work through this question as I read it. And I never read the whole thing straight up. I always work through it as I read it. I don't know. I think that really helps me. Okay, so we want to know the change in internal energy. We're given the energy as heat here, and we're given this volume expansion. So that means it's doing work because it's increasing in volume. So we're going to use the first law of thermodynamics, and this is it in all its glory. This is for a closed system, which is what we have here because the gas isn't escaping. We're not adding any more gas. Now we know the energy as work, Q, that's 1.3 times 10 to the 5 kilojoules. And it's positive because it's going into the system. So we want to keep this number positive. Now work is, I'm going to expand this. I'm sorry if this is small, if you're on a phone. I'm going to expand. So for pressure volume work is equal to negative P delta V, change in volume here. And this is true for a constant pressure process. And no other work can be done. Like there's no electrical work or nuclear work or anything like that, which is what we have. We're just expanding a balloon. So a gas is expanding. So we have pressure volume work. And P is the external pressure. It's always the external pressure. But in this case, it's also the same as the pressure of the balloon, we're assuming, because it's constant pressure throughout. The pressure inside the balloon is the same as the pressure out here. So this is negative 105. Now, we can be given any kind of units, and your prof will probably give you the wrong units in pressure because they like to do that. But when you're solving for work, pressure's got to be in pascals, or you got to convert it some other way. So I'm going to go straight to pascals. So that's times 10 to the 3 pascals here. Okay, because kilo means times 10 to the 3. Now, remember this delta V. Delta V is equal to the final minus the initial. That's what the delta means. So we're going to multiply it by the final volume, which is this one right here, 4.50 times 10 to the 6 liters minus 4.00 times 10 to the 6 liters. Okay, so that's the change in volume. Now, we want work to be in joules, right? Work's got to be in joules, or at least kilojoules. Here, this is in kilojoules here. So to get to joules, this needs to be in meters cubed. Like liters are not good. Liters are not good. We got to get in meters cubed. So there's a conversion, and you may be given this conversion. I'm just going to kind of straight up write it. We want liters to cancel out, so they're in the denominator. We want meters cubed in the numerator because that's what we want our volume to be in. And for every 1 meters cubed, that volume is the same as 1,000 liters. So that's our conversion right there. Okay, and for every, so now we're in joules because here we have pascals, liters cancel out, so it's pascals meters cubed, and 1 pascal meter cubed is equal to 1 joule. Okay, awesome possum. So, well, this is in joules, but this is in kilojoules. So what we're going to do is we're going to put everything in joules. So this will be 1.3 times 10 to the 5 kilojoules, and we want it in joules, so the conversion is we want to cancel out kilojoules, we want joules in the top, and for every 1,000 joules. That's the same as 1 kilojoule minus, and this minus is because it's the opposing pressure. As the volume expands, it's opposing the atmospheric pressure, trying to expand. 105 times 10 to the 3 pascals. And if I do this subtraction here, because it's quite easy, it's just 0.50 times 10 to the 6 liters, because this times 10 to the 6 just comes along for the ride, and we subtract these numbers. Let me know if that's confusing. I can make a video on that. And then our conversion comes along for the ride, 1,000 liters. Okay, awesome possum. So we'll plug that into our calculator. 1.5, 1.3 times 10 to the times 10 to the power of 5. I really like what these calculators where you can see what you type. You see, I noticed I typed something wrong, and on an exam that can like save you. That can be your saving grace for extra points there if you can catch yourself. Times 0.5 times 10 to the power of 6 divided by 1,000. And did I do everything right? Just like to double check. If you have a one-line calculator, you can't really double check your work. I think that's fine. I don't see any problem with that. Okay, so big number, but these are big exponents here. 1, 2, 3, 4, 5, 6, 7. 7.75 times 10 to the 7, and it's positive. 5 times 10 to the 7. Our units have to be in joules. Well, Pascal doesn't cancel out, actually. Just liters. Liters meters cubed is a joule, so this has to be in joules. We have 2 sig figs here. 5, 6, 7, 8, 3. We'll round it to 2 sig figs, I think. This is 3. Really, we only have 2 here, so we better be safe and just round it to 2. Okay, and this number is positive, which means the change in internal energy is positive. So that means even though, I'm going to go over here, so even though this balloon does work, it loses energy as work to expand, it gains more energy than it expends in work. So the more energy transfer, there's more energy transferred to it in heat as it uses up to expand. So it actually heats up. This balloon would get hotter because it's doing less work compared to how much energy of heat is going into it. Okay, this next exam problem is a slightly different take on those equations and the first law and work that we've been working on, and there's some different subtleties that you'll need to know for your exam, so have a look at this one. We have a gas that's compressed from 0.34 meters cubed to 0.15 meters cubed under constant pressure, 1.1 atm, and a temperature of 25 degrees Celsius. So we want to calculate the work, the heat, and the change in internal energy. So let's see what do we have here. So our initial volume is 0.34 meters cubed. Our final volume is 0.15 meters cubed. So it's being compressed because it's getting smaller. And we can kind of draw that here of what's going on. This is the gas, and this volume's going down. Oh, that's probably not the best way to write it. Maybe I'll write the arrows here to show that this is going down. We have a constant pressure, so that's important, of 1.1 atm. Again, we're in the wrong units, but that's okay. And a temperature of 25 degrees Celsius. Let's convert that to Kelvin right now, 298.15 Kelvin. Okay, so work, heat, and delta U. So we're going to start with the first law of thermodynamics for a closed system, of course, and we need to know all of these things. Now, do we know anything yet? What do we know? Well, we do know the change in internal energy, believe it or not, because this is constant temperature. So for an ideal gas, if the change in internal energy, not change in temperature, well, the change in temperature is 0, but the change in internal energy, it's also 0. The change in internal energy is 0 if temperature equals constant. This is like true, and you want to remember this. This is true for an ideal or a perfect gas. For real gases, it's not necessarily true, but this is true if your temperature is constant. Temperature is related to the kinetic energy of the gases, and since there's no intermolecular forces, essentially the change in internal energy is 0. So that's nice. This one is a big fat 0. So that's 0, basically 0 joules, 0 joules per mole or whatever. So we can plug that in. So we're a third of the way there. Now the heat energy transferred is heat. That's going to depend on how much work is done. So we don't have an equation for energy transferred as heat directly, really. We don't have an equation here. It is constant pressure, so maybe it's equal to the enthalpy, but we don't really have a good equation for that. We can work on the work. We can get the work. And since this is pressure volume work, we can say that the work is, and I'm going to write it down here what the work is to leave this question, this spot clean, is equal to negative P delta V. This is true for a constant pressure process as long as the pressure is the same as the external pressure. And okay, so we'll plug that in. So pressure is negative 1.1 atm. Now atm is a bad unit for if we want, because we want things to be in joules. It's not a bad unit, but it is if we want things to be in joules. So we need to convert to pascals. So we'll put atm down there to cancel out, and we'll have pascals up here. And for every 1 atm, there are 101.325 times 10 to the 3 pascals. Okay, so that's in pascals, that's good. And then the change in volume, that's volume final minus volume initial. Volume final is 0.15, 0.15 meters cubed. I always like putting in the units, always recommend that, 0.34 meters cubed. Okay, negative 1.1 times 101.325 times 10 to the power of 3 times 0.15 minus 0.34. Does that look good? Looks good, I guess. Yep, okay. And okay, it's a positive number. So 71177. No, 212177. Is that right? 21177. 2117. Remember, it's very early in the morning still, but I am pretty stoked to go through these things. I was thinking about it all night. Okay, this is a positive number. So what does that mean? I'll just put the sig figs here. It's significant to 2 sig figs. It means that the system's gaining energy, and it's gaining energy from work. Work energy in the form of work is being transferred to the system, and that's true because we're putting work into the system by compressing the gas. So that's a good sign. So this is the work, and that's our answer for work here. So we got this one. We got the work. We'll just answer it in, yeah, we could write it like this, or we can say it's 2.1 times 10 to the 4 joules, or say 21 kilojoules. Either one should be okay. So that's cool. And lastly, we need the energy transferred as heat. So we'll plug that in. We got 0 for the internal energy previously. We're solving for Q, and we know that the work is 21 kilojoules. Does it care if we want it in joules or kilojoules? No, it doesn't care. So I'll just use kilojoules since it's not asking for a specific unit. Now this is like pretty easy to solve. The Q is equal to negative 21 kilojoules, and that's our answer. And before you go on to the next killer question, before you move to the next spot, just let's think about this. Does this make sense? Well, if the change in internal energy is 0 if it's not changing, so it's the same temperature, same kinetic energy of the molecules when we compress the gas, we're putting energy into the gas in the form of work. So the system is gaining energy as work. But if it's gaining energy as work, the internal energy should increase. Since the internal energy is not increasing, that means we're losing energy. The energy gone in as work has to go out as heat. So we have work energy going in and energy being transferred as heat out, heat transfer going out. So the energy in equals the energy out. That's why the heat transfer out, negative, which means it's lost by the system, is the same as the energy gained by the system in work, which means the change in internal energy is 0. Okay, this exam problem gets students all the time, but it's not going to get you because I'm going to explain it, the whole thing. So we have this gas, it's expanding into a 1 liter vacuum. So this is like 1.0 liters, and we have like a gas here, and it's expanding into this 1 liter volume, essentially. And a vacuum contains no gas, and thus has no pressure. And you might not be given this hint on your exam. I just put it in there just to make it pretty explicit. So basically the pressure equals 0. And this is like the external pressure in some ways. It's like external to the system here. If we just ignore the outside surroundings here, so there's no pressure. There's no pressure because there's no molecules here, or there's no spring pushing on a piston or anything like that. And we have a temperature of 298 Kelvin. So there we go. How much work is performed and why? Well, we don't have too many numbers to deal with. We have an equation for work. Work is negative P delta V, right? Negative P delta V. Now, this P, this isn't the system pressure. It's only this system pressure if it's the same pressure as the outside. This is the external pressure. This is always the external pressure because this is the opposing force. That's why the negative is here. We only say that this pressure is the system pressure, like the pressure of the gas. This pressure is only the pressure of the gas if the pressure is constant. Then we can say that the outside pressure is the same as the inside pressure. But in this case, it's not the same. We don't have a constant pressure process. As this gas expands, the pressure is going to decrease. And so this pressure is truly the external pressure and not the pressure of the gas. Well, what's the external pressure? It's the pressure that the gas is expanding against, and the pressure that the force that the gas is trying to push against is basically non-existent. There's no force. There's no external pressure. It's not pushing anything to expand. This is zero. So the work done by the gas, even though it's expanding and going into a larger area, is zero. So basically 0 joules. It takes no work for this gas to expand because it's not pushing against anything. There's no external pressure. Okay, now on for our killer exam problem. And if you can do this and understand everything that I go through, then you should be like super good. You should be killer yourself at this problem, honestly. I'm going to go through it nice and slowly. Okay, so this is a calculate the work done. So work is W, and the change in internal energy for the reaction of, now we have a certain amount of grams, 2.3 grams of SO2 under constant pressure. So that's nice. Pressure is constant, 1.1 atm, and a temperature of 325 Kelvin for the reaction. Now, delta U, to get the change in internal energy, we need to use the first law of thermodynamics for a closed system. So this is it in all its glory. We've seen it many, many times before. And we're given the change in enthalpy. Now, it's very important to look at these units too. Kilojoules per mole. Now, some people may leave out the per mole, but this per mole is very important, especially in this question. This means per mole, but per mole of what? It's per mole of the reaction. So if 2 moles of SO2 reacted with 1 mole of O2 to give 2 moles of SO3, then it's like this reaction happened once. Kind of 1 mole of this reaction happened. So that's what this would mean for per mole. But we don't care about per mole of the reaction. We care about moles of SO2 and eventually grams of SO2. So we're going to divide everything by 2 so that we have this in terms of 1 mole of SO2. So I'll do 1 mole of SO2 plus, now this would be a half mole of O2 goes to 1 mole of SO3. I don't have to write the ones in here, but it's kind of nice. Now, since we have half the amount of moles reacting, we'll produce half the amount of energy as heat. So the change in enthalpy will be half the amount. So this divided by 2 is negative 99 kilojoules. Now this is still kilojoules per mole, right? Kilojoules per mole of the reaction. But for every time a mole of this reaction occurs, we use up 1 mole of SO2. So this is equivalent to kilojoules for every 1 mole of SO2. I hope that makes sense. Okay, we're going to do something very similar with work as well. So we can't get the change in internal energy yet. We need the work. So we have our equation for work. Work equals negative P delta V. But unfortunately, we don't have any information about the change in volume. Although these are all gases, we'll assume that they're ideal gases. So PV equals nRT. And if pressure is constant, then pressure times the change in volume is going to equal to the change in moles. And the moles are changing because for every, this is like a 3 to 2 ratio. For every 3 moles of reactants that react, we get 2 moles of products. So the moles of gases are changing as we go from reactants to products. R is a constant and temperature is a constant. See, temperature is a constant here. So we could literally substitute this in. So negative, rather than P delta V, we'll write in delta N RT. And we're going to use this equation here for the change in the moles. And I will explain it thoroughly. So our change in moles, maybe I'll do it over here. That's, as always, moles final minus moles initial. But finally, the number of moles we have are all products. So it's moles of the products minus moles of the reactants. And if we use this equation here, the products are 1. So that's 1 mole minus the reactants, which is 1.5 mole. Okay, and then R, so we want to use the right R, the R with joules, 8.3145 joules per mole Kelvin. And the temperature is 325 Kelvin. Okay, so it appears that these not joules. The Kelvin cancels out, of course, but it appears that these moles cancel out. And if those moles cancel out, what we're left with is, I'll just put this in, this would be negative 0.5. It's not too hard to do in my head, times 8.3145 times 325. Does that look good? I think that's good. Okay, so 1351.1, 1351.1 joules. And does this make sense? Well, if we have like a piston with a gas, and this is our gas in here, these are the reactants. When they turn to products, we get less moles. The number of moles gets reduced. So the volume has to go down, which means work is being done on the system. We're putting energy as work into the system, so the system's gaining energy as work. That's why this is positive here. So that makes sense. Now, is this how many joules of work that this many grams of SO2 does? Think about it. Did we even use the 2.3 grams of SO2? No. See, we used a balanced equation. We actually only looked at 1 mole of SO2. So technically, this is how many joules of work would go into the system if 1 mole of SO2 reacted. So this is really joules for every 1 mole of SO2. Joules per mole of SO2. I hope you get that. I can do another video to explain this a little bit more. But here we have kilojoules per mole of SO2. So we have the change in enthalpy. We have the work done. We can get the change in internal energy. Now this is the heat, but energy transferred is heat. But under constant pressure and with PV work only, the change in enthalpy is equal to the heat transferred as work. So that's under constant pressure. So we can literally just substitute that in. I derived this in another video as well, but it's probably just something you just kind of need to know. So delta U equals, it's a funny looking delta. Let's see here, delta U equals our delta H plus the work. And our delta H is negative 99. Now we're in kilojoules. So I'll put this into joules, times 10 to the 3 joules, because there's 1,000 joules in a kilojoule, plus 1,351.1 joules. You know, this is a lot of digits here. We only have one significant figure in this, unfortunately. I'll make it 2 for now, but really there's only one. Okay, I don't know if your teacher is that big of a stickler or not. Times 10 to the power of 3. Plus 1351.1. So, okay, yeah, I was just seeing if this makes sense. This is a much larger number, the heat transferred number. Okay, so negative 97649, 97649, rounding, negative joules. So that's the change in internal energy. We'll write it as, say, 2 sig figs, 9.8 times 10 to the, actually it would be 3 sig figs because this is such a much bigger number. 1, 2, 3, 4 joules. Okay, so this is joules. Now, this is joules per mole of SO2, right? So this one here, I'm going to zoom in. This is joules per mole of SO2, and this is joules per mole of SO2. That means the internal energy is also in joules per mole of SO2. Joules per, I'll get rid of the box here. Um, get rid of the box per mole of SO2. But we really don't care about moles of SO2. We care about grams of SO2. So we need to convert the moles to grams. So we have 2.3 grams of SO2 reacting. So we're going to start off with the change in internal energy here, negative 9.8. Oh, we need to do the same for the work as well, don't we? Okay, we'll do that after. Times 10 to the 4 joules for every 1 mole of SO2. And we will multiply this by a fraction. And we want moles of SO2 to cancel out. We want grams of SO2 downstairs. And based on the molar mass, I got here, molar mass of SO2 is 64.066. So 64.066. You'd obviously would have to add it, add it up on the periodic table, but I just Googled it. So that's per gram. No, this is per gram of SO2, but we don't have a gram of SO2. We have 2.3 grams of SO2. Actually, I'm going to do it in 2 steps, just so it's clear. So we're not really skipping anything. So 10 to the power of 4. We should use one more digit, actually. We'll round at the end. So 9.7649 times 10 to the power of 4 divided by 64.066. Okay, so negative 1524. Negative 1524. That's joules. I almost wrote grams there. That's joules for every gram of SO2, for every 1 gram of SO2. Well, we have 2.3 grams. So we got to take this number, 1524 joules for every 1 gram, and multiply it by however many grams we have, 2.3 grams of SO2. Okay, so here we are. So negative 1524 times 2.3. So negative 3.5 times 10 to the 3. This is grams of SO2. I'll put the, there. Okay, 3.5, negative 3.5 times 10 to the 3 joules is produced of internal energy for this here. Okay, let's do the work. So the work was 1351.1. So work is 1351.1 joules per every mole of SO2. And we need to get to grams, so we'll multiply this by the moles divided by the grams using the molar mass, grams of SO2. 1 mole for every 64.066 grams. And now that we're in grams, we just need to multiply this by the 2.3 grams of SO2. Okay, so we'll plug that in. 1351 divided by 64.066 times 2.3, and 48.5, 2 sig figs, 48.5 joules of work performed for when that 2.3 grams of SO2 reacted. Okay, hope you enjoyed it. I know this was a long problem, but we did go through a lot of points, touched on a lot of subtleties that your prof may have glossed over or it may not have made sense at the time. I really hope it makes sense now. Thanks again for watching, and I'll see you in the next video. Cheers.